In this video, we're going to talk about the normal distribution. The normal distribution is a specific continuous distribution that is bell-shaped and symmetric. And the reason we're focused on this is most of the situations that we're going to encounter for the second half of this course are going to be normally distributed. The graph of this distribution is called the normal distribution curve, or more simply, the normal curve. You'll see the equation for the normal curve below, and it is ugly. You will never be expected to use this or memorize it, but it is good to see that it depends on two important population parameters. The first familiar population parameter I see here is the symbol mu, which I know stands for the mean. The other symbol that I recognize in that formula is the Greek letter sigma, and I know that that stands for the population standard deviation. You'll notice there are a couple of other symbols that pop up in that equation. Pi is a constant. We know that it's approximately 3.14. E is also a constant. He's called the natural base. And he's about 2 point something, and I don't remember what the decimal looks like off the top of my head. The important thing is that my two variables, my independent variable x, my dependent variable y, are related by the mean and standard deviation. Everything else in there is just a constant. Let's take a look real quick at what those two things do to our curve. If we change the mean of our distribution, what we're doing is we are moving the center of that peak up and down the number line. So changing the mean shifts the entire curve left or right. If you remember from our previous math class, we would call that a translation. We're not changing the shape of the curve, we're just sliding it from side to side. Whereas the standard deviation is going to change the shape of the curve. The math term for that is a dilation. Changing the standard deviation makes the curve wider or narrower. That should make a little bit of sense since we understand what the standard deviation is a measure of. Standard deviation measures the spread of the data. So if my standard deviation gets bigger, I would expect my data to be more spread out and my curve to be wider. Whereas if my data has a small standard deviation, it's clustered closely about the mean, I would expect that my graph would be narrower because all of those data points should be close to the center. There are a couple of other properties we need to know about the normal distribution. First, it is unimodal, meaning it only has one peak, and that peak is where the mean, median, and mode sit, because all three of those measures of center should be equal in a normal distribution. Our graph is symmetric and unimodal, so all of those measures are right on top of each other. And it is symmetric about that measure of center, meaning if I fold my graph in half at the mean, I should get two perfect mirror images. That's going to help us a lot when we start looking at probabilities later this week. The next two things, we know that this curve is continuous. So we use the normal distribution to describe the behavior of normally distributed continuous random variables. And in this continuous graph, the x-axis forms an asymptote. And I don't expect that you remember that math vocabulary term. That's more Algebra 1, Algebra 2 vibes. But if I scroll up and we look at this picture of a normal distribution here, I can see that on the left and right edges of the graph, that curve is getting lower and lower and lower, closer and closer and closer to the x-axis. It's never going to touch or cross it. And that is what an asymptote is. Knowing that this graph never closes off at the edges makes the next point a little bit odd. Even though this graph goes on forever and ever and ever on the left and right, and it never closes off, there is a finite total area, and we know that it's equal to 1 or 100%. I'm going to ask you to take that on a leap of faith here, because in order to prove that, we have to come back up here to this ugly equation and do some calculus level math, which is beyond the scope of this course. So we do know as mathematicians that the area under that curve is 1 because we can do calculus on its equation, but we won't do that in this class. All you need to know is that the area under this curve, which represents probability, should add up to 100% or 1, because this is a probability distribution. The last thing we need to know about the normal curve is that the distribution of data within a normal distribution follows something called the empirical rule. And if we look more closely at this picture, you'll notice that the axis is labeled with the mean in the center. And then as we go outward from the center, we're adding and subtracting 1 standard deviation in each direction. So from each red mark, it's plus 1 standard deviation, plus another standard deviation, plus another standard deviation. Going the other direction, we're subtracting 1. Subtracting 1, subtracting 1. And based on this curve as described by standard deviation relative to the mean, we know where our data sits. If this curve is in fact normal, about 68% of all of the data should sit within 1 standard deviation of the mean. So this right here represents just under 70% of all of the data, more than half. If I go out another standard deviation in either direction, I know that about 95% of all of the data is within 2 standard deviations. So at this point, this is almost everybody. And we talked a little bit about outliers before. Outliers are data values that are extreme when compared to the rest of the set. They don't generally fit a pattern. 2 standard deviations out from the center is another way to classify outliers. If you're out in this tail in a normal distribution, you are sometimes called an outlier. If we go out 1 more to 3 standard deviations on either side, that's almost everybody at 99.7% of our data. Sometimes in other textbooks, this is called the 68, 95, 99, 7 rule because of that predictable distribution of data. We can use this to help us figure out probabilities without having to use a calculator. Now that I know there's about 68% from 1 standard deviation to 1 standard deviation, and I know the mean cuts the curve exactly in half, that tells me that there should be about 34% and 34% on either side. You can use that idea to fill out the other sections of the graph. But what I'm going to do in a later video is show you how to use your calculator to find those probabilities. The empirical rule is more helpful to help us verify the data that's coming out of our calculator. Does what the calculator says make sense in terms of the picture that we draw? All right, if you have any questions on this video, feel free to send me an email or drop by office hours. Otherwise, I'll see you in the next video.